Hello, folks. Here we are with the second part of Chapter 7 on data frames. This screencast will be divided into two parts on data frames. So how do we deal with data sets in R? Well, what is a data set in the first place? A typical data set might be like this row-column format that you might see in an Excel sheet. So here we have information on characters in The Wizard of Oz, where each row is a particular character, and the columns provide different types of information about the characters, their names, their ages, desires, Kansas, brains, heart in the case of Tin Man, and so forth, and whether or not the person likes dogs. Everybody has an opinion about dogs, I guess, except Toto, whose value here is an NA. That's an example of a tidy data set. We say that a data set is tidy when every row corresponds to a unique entity of the same sort. Another name for a row is a case. Another name you'll see is an observation. Also, for data to be tidy, every column has to record values with the same type of information. So, like the ages, they're all double precision numbers. Desires are all characters, strings. Likes dogs is logicals. So keep these definitions in mind for your study. So you might wonder, couldn't you just use matrices to store the data in a data set? After all, they're two-dimensional. They have rows and columns. But you cannot do that because matrices are simply atomic vectors with the row and column attribute added on. So atomic vectors, remember, can only handle one type of data at a time. You can't have both logicals and characters and numbers, in an atomic vector. And a data set can have lots of different types of data in those columns. That's the case for the companions on the yellow brick road, where column 1 is probably character vector, age is a double precision vector, desire is another character vector, and likes dogs was a logical vector. So it would be really nice if there were a non-atomic two-dimensional data structure in R, so that these columns could have the types that we need them to have. That's where data frames come in. Yep, we really have good news here. R has the data frame as a flexible two-dimensional data structure. So the formal definition for data frame is it's a two-dimensional data structure in R in which the columns are atomic vectors that can be of different types. So let's work with a simple example data frame, the M111 survey data frame that is in the package BCSCR, Beginning Computer Science with R, that I have written up for you and which is installed on the server. You can attach that package to your search path with the command library bcscr. And then you can get a look at it. We'll go ahead and go back to RStudio and actually look at the look at commands ourselves directly. So once you have attached BCSCR, M111 survey is going to be on the search path, and you can ask to view it. And what you'll get in the editor pane is essentially an Excel spreadsheet looking representation of the data frame. What happens here is every row is a person on whom some information has been recorded, And every column is the different type of information, like the height of the person, the height that the person would like to be ideally, how many hours of sleep the person says they got last night, and so on. Now, you might wonder, how do I know those things about the data set just from the view? And the fact is I don't. But you can get help on any R object that's on your search path by just putting a question mark before the object name and running that command. And over in the lower right-hand pane, the help tab is now on top. And what we've got is a little help file that comes along with the BCSC-R package, and it tells you about M111 survey. It tells you what each of the columns represent. It also tells you that this was a survey of Math 111 students at Georgetown College. Basically, it was one fall semester, I think maybe the fall of the year 2011. At the bottom, we learn there are 71 rows, so there were 71 people in the survey, and 12 columns. That means that we got 12 pieces of information from each of them. So help is always very useful. You can try it out on all kinds of R objects. Now, there's other ways to see a data frame other than the view. You could just print it all out to the console, but then the entire data frame would spill out and scroll past you, and it would be very hard to see it well. If you wanted to see a small part in the console, though, you could use the head function. The first argument is the data frame that you want to see the head of. The second argument in says how many rows you want to see. And so this will give you the first 4 rows. There's a lot of columns in this data set, so they kind of spill over into a second row to finish up. So it's still a little awkward. You can get the structure of a data frame with the command str. And this tells you 2 things. Structure always tells you 2 things. The kind of a thing it is, a data frame, and then an account of the parts of the thing and the relationship that the parts have to each other to make it the kind of thing that it is. Now, the parts of this data frame are its columns, the height column, the ideal height column, the sleep column, and so on, that comes past these mysterious dollar signs here. And the relationship between them is that they all have 71 elements in them, and those elements go with each other. So like the 76 for the height goes with the 78 for the ideal height. There's a person who was 76 inches tall but wished they were 78 inches tall, and so on. Now I want to go back to RStudio and show you a little trick. If you've got some data frame off in a package somewhere and you'd like to get more easy access to what it looks like, then run the command data quotes the name of your data frame. And that'll load the data frame directly into your global environment. It does it at first on a promise, but if you ask to work with it in any way, it'll fully come into the environment. So for example, let me just press on it right here. And oops, I lost my file. Let me get it back. Here we go. And so we get that little description. And now if we press the little blue button next to the data frame, the structure actually pops out for us. In addition, if we were to press just the data frame itself, then we get the view. So if you've got a data frame directly loaded into your global environment, you can work with it nicely in those ways. The blue button gives you the structure, direct press on the name gives you the view. If you want the names of the columns, then you can get it with the function names. There's a little character vector of length 12 that comes out. But what you want to do the most is get at the columns that are inside the data frame. You can use a $ to do this. Name of the data frame, then the $, and then the name of the variable you want to look at. So if you want to see the fastest speeds, you could do that by evaluating this expression in your R session. So let's head back and let's just run this command. First, I'll move this over to the side, and I'm going to run M111 survey fastest. And down here in the console, there appear all of the fastest speeds. Fastest, as when you read the help, turns out to be how fast you drove a car in miles per hour, at the fastest you ever drove a car. So that first person apparently drove their car at 119 miles per hour. Now this is a vector, so you can work with it like you work with any vector at all. You can do anything you want with it. So for example, you could subset it. You could ask for the first 10 places of it by just putting the selection 1:10 after the name of the vector. And that's the fastest speeds ever driven by the people in the first 10 rows of M111 survey. It's a vector, so you can do anything you want with it. You can take the mean of this numerical vector with the mean function. I'm throwing in that parameter not assigned dot remove is true, just in case somebody did not answer the question about how fast they drove a car. The NAs would get knocked out when you compute the mean. So on average, our 71 students drove 105.9 miles per hour at their fastest. This next example shows me taking the fastest speeds and selecting for where the fastest speeds were bigger than or equal to 150 miles per hour. I only get 2 speeds. Now, when we looked at the structure, we saw that there was something interesting about the types of variables that we had. Let's head back to RStudio and see that again. So, looking at M111 survey structure, height is said to be a numerical variable. Ideal height is said to be a numerical variable. In fact, there are double precisions in R, and num is just a way of saying that. Sleep is another numerical variable. Fastest speed ever driven is of integer type, and I guess that's because when people answered the question about fastest they ever drove, nobody said any decimal answers. They all gave whole numbers, so that came in as an integer vector. But then there are some other variables that are said to be factors, like weight feel. So that's how do you feel about your weight? The 3 possible answers were 1, I feel underweight, 2, I feel about right, 3, I feel overweight. It's said to be a factor with 3 levels. Love first is a factor. Extra life is a factor. So enough sleep and sex are a factor. What's up with factors? What are they? So factors are a way that R handles some categorical variables. Now, categorical variable is a variable whose values can't be expressed meaningfully by numbers. Your height can be expressed meaningfully by numbers. The fastest you ever drove a car could be expressed meaningfully by numbers. But like where you prefer to sit in a classroom, do you prefer the front, the middle, or the back? Cannot be expressed meaningfully by numbers. I mean, you could code them as 1, 2, 3, but those numbers don't really naturally go with where you prefer to sit. It was just a way that we hooked them up. So when you see a factor variable, you're going to see the set of its possible values as its levels. And when you've got a factor, you can put it into the R function levels, and it'll give out the levels as a character vector. So you could actually make a factor out of an ordinary vector. Here's Oz faves, my favorite Oz characters. Glinda, Toto. Toto again, Dorothy, Toto, Glinda, Scarecrow, Dorothy. I could make a factor out of it by just saying factor of Oz faves. So this new variable here, factor faves, prints out a little differently from an ordinary character vector. There aren't any quotes to indicate the strings. Just give the various values. And the levels are the 4 unique names that actually showed up. Now you can actually set the order of the levels to be any order that you want. By default, it's going to be R's notion of alphabetical order. But if when you made a factor out of Oz faves, you took a second argument, levels equal, and then you put the 4 possible values in the order that you want, here with the C command, then you get the same printout of the various names, but the levels come in that different order that you specify. You might wonder, like, why is this important? We'll see in Chapter 8, when we do various data analysis work, that it can be useful to have your factors come in a desired order. Now, not all categorical variables should be represented as factors in R. Basically, if your categorical variable does not have a lot of different possible values, it's okay to let it be represented as a factor. Like, think about sex. So you have your 2 most common sexes, male and female, and there might be like a third possible answer, other, for intersex or something like that. Or favorite sport, if people were asked their favorite sport, there might be, maybe 15 or 20 different possibilities. That's not too many. But what would be really bad as factors is if you were taking data on people and you were recording their street address. Almost everybody in the data set would have a different street address. Or how about if you asked them for their favorite quotation? Again, almost everybody would have a different favorite quotation. Then it wouldn't be a good idea to make your variable into a factor. There would be none of the advantages of factors come along with it. There would be no savings of space and things like that when the data set is stored. So if you ever have a factor that you want to make into a non-factor, just take it and put it in as an argument to the as.character function. So, for example, factor faves can be taken right back to the original character vector in that way. So you can look at data frames that have already been made for you in packages that you attach to your R session. But can you make them yourself? And the answer is yes. There's essentially 2 ways to make a data frame. You can create it directly from vectors, and we're going to learn about that here. Another way is if you've got a couple of data frames already, then you can bind them together to make another data frame that's bigger. You can bind them by their rows or by their columns, depending on how they look. And if you like, you can read about that in the book. It won't be necessary for any of our homework in this chapter. So how would we create data frame directly? Let me head back to RStudio and show you how this might look. So say I've got character vector of length 3 called n, and it's the names of my people. And this next numerical vector called height, which I will now get into my global environment, is the heights of those people in inches, let us say. And this third vector, a, is going to be the ages of these people in years. And then we can use the data.frame command to make a data frame from those three vectors. What we do is each argument, what comes before the equals, is going to be the name of the column. What comes after the equals is the values that will be in that column. Osfolk is going to be bound to the result of that call. Here it is in our global environment. And so if I look at its structure, I see, indeed, I have a name variable, a height variable, and an age variable. If I ask for a picture of it in the view, by clicking on Osfolk, then I see the data frame in row column format. So Dorothy was 12 years old in The Wizard of Oz. I don't know how old I have a mistake here. I actually have an error. The Scarecrow is the one who was supposed to be 0.04 years old, because if you read the book, you find that he was actually like put out into the field 2 weeks before Dorothy found him and removed him from his stick. And I was going to guess that the lion was 18 years old because he seemed like kind of a teenager. Well, I have a mistake there in my code. Let me go ahead and just like fix that right now. Sorry, I'll fix it in the slides too, I guess. But if I put an 18 here for lion and a 0.04 for the Scarecrow and rerun that for A, and then rerun Osfolk, and then take a look, now it got it right. Sorry about that. So the one thing you noticed when we looked at the structure was that the names came in as a factor with 3 levels, Dorothy, Lion, and Scarecrow. And we said it wasn't a good idea to do names that way. So could you get out of that? Well, one thing you could do is you could directly turn the name variable in the Osfolk's data frame back into a character vector. So here we are saying that Osfolk $name shall be as.character of Osfolk $name. And then the result would be, indeed, just a character vector for the name. But another possibility is that when you create the data frame, that you don't let those character vectors turn themselves into factors. You do that by throwing in an extra argument to the data.frame function, strings as factors equals false. And so if I do that, I've got a character vector for the names right away. That's all for this part of the slides. I will be correcting the error in the slides that you actually work with.